Hello everybody. So this is a continuity of the financial time series using the MATLAB. So we're going to talk about the autocorrelation function. In short, we have ACF, autocorrelation function. So the other measurement of serial correlation can be the partial autocorrelation function. Right? But today we're going to focus on this. So for the autocorrelation function, basically it try to measure the possible serial correlation between the lax value, okay, of a series, which how is it going to influence the current series, okay, in terms of, let's say you have xt. So the autocovariance function, okay, before we go to correlation, we have covariance. So you have a gamma x, let's say, with a lag of h, So we just use the COV to represent the covariance. So you have xt plus h to xt. Okay, so this, as long as lags between the two axes here, which is a stationary time series, then this is a lags between two. Okay, so of course this is also possible if you have a covariance, let's say xt and x, let's say t minus h. So the lags between these two series is also h. Okay, this is also h. So the autocorrelation function, which is derived from the covariance. Okay, so you have a covariance h over the variance of the series with a lag of 0 means the variance. Okay, so this will give us the correlation between the xt plus h and xt. Okay, in a if you're given a sample value, okay, instead of this is the so-called population autocorrelation function, okay? So if you're talking about a sample data, then you have a sample autocorrelation function. So this one basically will sum up the multiplication between, let's say, t to the terms k plus 1. So there are two terms here, yt minus the average value, y bar. And then this one, normally we have y, or you can use the x or t, whatever the series you want to name this. Okay? So the x or yt can simply representing the price index, the return series, or even the volatility series. Okay? So this is t minus k. In most of the data set, we don't actually have the so-called plus h. The plus h basically is something forward. So you only have historical data. Therefore, most probably the data is t minus the k alone, or the lags minus the h, the average value here. Okay. So then the whole thing divided by the variance of t, summation of t equal to 1 until yt minus the y bar. Okay, so this will be the sample. So this is sample ACF. So this is a population. Okay. So this is in short the formula to obtain the values. So if you plot, let's say you have a white noise, okay, you try to plot it, so it end up to have ACF or sample ACF, which, so you have two boundary here, okay? Boundary. So this is a 95% confidence level boundary. So in short, if you have a white noise, which is a random process, so you should expecting the ACF of R1, R2, and so on, right, up to R40. So it will fall within this 95% boundary. This means there is no significant spike of any lags related to the autocorrelation. So any K here, let's say up to 40, okay, this is the K, are all not significant, okay, statistically at 95% confidence level. So this will be the exact value of each R. So the 0 here actually representing the variance. Okay? So the variance of X basically should be always equal to 1, okay? Because the correlation is covariance over the variance. So if H is 0, so variance over variance, we should get a 1 all the time. Okay, so the leg 0 is 1, leg 1, leg 2, leg 3, and so on and so forth. So from this ACF, we also able to observe that if you have a seasonality data like this, where it repeats and repeats and repeats. For example, the sales of beer during every December, you should have a peak selling a month every year, okay, repeating. So the ACF actually can provide these repeating patterns in this particular way. Okay, so this is a sample ACF we have. So for trend, you might see positive and negative trend might be different. Okay, but somehow if you look at this one, basically these two are the non-stationary series. So for financial data, if you talk about the price index and the returns index, so this one basically is come from the RT, basically is the ln of PT minus the ln of PT minus 1. So this returns, the price index obviously have a trend, upward trend, maybe a downward trend, upward trend again. Okay. So when you do the first difference about this data set, then you will actually get a stationary process. It's actually quite similar to a white noise, okay, but it is not. So you can see that you have so many significant spike over the 95% boundaries, okay, almost all of them, as compared to after the first difference, there will be no even one significant spike in the first 40 legs. Okay, so therefore this is the what is about the what you can actually observe from the observe from the autocorrelation function. Okay, so what are we going to do with the ACF and also the PACF is from the ACF basically we actually can use it to identify the presence of moving average and even the autoregressive model as well. So for MAQ depends on the legs, then you will see a cutoff of the Q legs. Okay, so you see some significant spike. After the Q, it will become not significant. Okay. On the other hand, the PACF can be used to identify the regressive models. Let's say after the P legs, there will be no more significant spike. Okay, we can use the ACF and PCF to identify this. So we're going to use a function called autocall and parcall to identify this. Okay, so after this, we should be able to see the how we can use the ACF and PCF to identify the possible models in financial crisis. Okay, so let's go to the coding we have done previously, the simulate AR model, ARMA model. So we have actually pure MA, leg 1, leg 2, pure AR, leg 1, leg 2, and also the ARMA 1, 1 models. Okay, ARMA 1, 1 model. So we just stick to this. Then let's say instead of plotting this, we can actually combine the autocorrelation function and the partial correlation function, both of them. Okay, both of them. So you can just put it here. combine both of them. So we actually have, let's say, ACF, sorry, ACF and PACF plots, okay, for MA1. So this one is quite straightforward. You can use a figure because we want to generate a new figure. So we use a subplot here. So you have 2 row and 1 column, 2 row, 1 column. The first graph, which is the auto call. So the function is called auto call. Okay, auto call. So we have MA01, isn't it? So this is MA1. Okay, MA1. Okay. Then we just put a title ACF for MA1. Oops, sorry. So we can just put another one, subplot. Now we go to the PACF, 2 row, 1 column, the second graph. Okay, so the same thing, we use a par call, MA1, then put the title again, a PACF, MA1. Okay, so now we can run this and have a look. Okay, so we just run this and have a look. Under the editor, you can run this. And look at the graph and have a look. So this is the 5 era 1. Okay, so now we have this MA1 models end up to have the ACF of MA1 is, so you can see there's a leg 0 is always 1, leg 1 is significant, then the rest of the red point here is actually all fall within the 95% boundaries. So PACF also showing the similar result. But if you go back to the slide, for identification of MAQ model, we always refer to the ACF. Okay, so this one we refer to the ACF. So MA models we refer to ACF, AR model we refer to PACF. So in this case, the MA models we refer to the ACF. So ACF, there's one spike means the moving average with order of 1. That might be the, if this, because it is a simulated series, isn't it? So the MA1 should have 1 spike. Okay, if you do not believe, then of course we can prove this analytically afterwards. Okay, but now we just go back to the coding here. Now we try the MA2 and see what happens. Okay, we can just copy and paste this, and then we just go to here. This is the second graph. So we have MA2 now. So this is same one, but this change it to 2. So in this model, we're expecting to see what? To see 2 significant spike in the ACF. Okay, 2 significant spike. So now we can just run this. We just change the MA1 to MA2 because our MA2 is the AR MA2 models. Okay, so this one you can just go to editor and run this one more time for MA2. Okay, this MA2. So this AR2. So you can see how many spikes here? 1, 2. Okay, and then after that, all the legs after that will be fall within the 95%. Of course, there are some points actually on the line of this 95% boundaries. But the very significant plots you can see here in ACF, MA2 you have 2 spikes. So similarly, if you have MA3, MA4 and so on and so forth, you should have MA3 you should have 3 spikes, okay, which are significant. Okay, so this is one way to identify the possible AR or MA models. Okay, so why the ACF behave in this way? So we'll show this in the next session, where we will analytically show that how we get this spike, and after that the ACF will be all 0. So now we shift to AR model. We can use a similar methods here. Just copy and paste. Then we go to an AR1 model. AR1 model. So we just change this to simulated. Sorry. So just now is this. Copy and paste this. Okay. So this is ACF for AR1. Right? So this is AR1. This is AR1. This is AR1. This is AR1 this way. Okay. So now we run this and have a look under the editor. So you see this is not the one we want. Okay, so this is AR1. Okay, sorry, this is AR1. I think something wrong. The labeling is wrong. So you can see for AR models, we actually look at what? Look at the PAC. Okay, AR model PAC, because there's a cutoff of ACF, PACF after that. So you look at this graph just now. So there's only one spike here. Then one spike. So you're expecting AR2 should have a PACF for 2 spikes. Okay, 2 spikes. So we can just show that whether this is true or not. So you can just go to the AR2 here. You just copy and paste this. Okay, this AR1. So this is just to prove that in terms of graph, you should see this value. So this AR2 to okay. So now we run it one more time. You're able to observe that this is the AR2 model. Okay. So for AR model, we look at the PACF. So there are how many spikes? 2 spikes. So we can see the ACF on the other hand, the ACF is actually reduced, decaying gradually, okay, to close to 0. So this is actually fulfill the condition, tails off gradually for the ACF or AR models. So because this is what we have simulated, okay, this is what we have simulated, therefore it should provide the 1 spike or 2 spike from the simulated AR1. Okay guys, so this is what I like to show here. Okay, so after this we will look at some analytical way to show that why MA1 have only 1 spike and why AR1 have a gradually reduction of the magnitude of ACF. Okay, for ACF MA1 have a 1 spike, but the ACF for AR models actually have a tails of gradually, right? Tail off gradually. Okay, so this is what we're going to show in the next session with analytical way. Okay, till then, bye bye guys. So hopefully you will join the class afterwards.